All right, welcome to chapter 19, amine chemistry. Okay, so the first thing we need to do is we need to be able to classify the nitrogen containing functional group on an amine. And this is important. We provide an acceptable name. We have common names and we have regular names. But by classifying them, you're going to understand kind of what reactions they're doing. So this first one, because this nitrogen has one carbon attached, so you find your nitrogen, and it has one carbon attached, that makes it a primary amine. And the name of the first one could be, we'll put the name here. You find your longest chain, so that would be 1, 2, 3. So 3 would be propane. You drop the E, and you could add 1 amine. So it lets you know that the amine group is on the carbon number 1. And then you'd have your substituents, which would be 2,2-dimethyl propane 1-amine. Okay, the next one, you find your nitrogen, and you see it has 2 carbons, so that would be a secondary amine. And you find your longest chain, so we have 1, 2, so that would be ethane, drop the E, add the 1 amine. But then you notice the substituents here on carbon number 1, you have 1-methyl. And when you have a methyl group on the nitrogen, instead of using numbers, you would do -N-methyl. That's how you do that. Okay, your next compound here is would be considered classified as an aromatic amine for the nitrogen, and that is pyridine. So you can look at your slides with your in heterocycle. So when you hear heterocyclic, that's a cyclic molecule with an atom that's not carbon. So you're like oxygen, nitrogen, sulfur. That would be a heterocyclic. So here you count this as 1, 2, 3, and that would be named 3-nitropyridine. That would be an acceptable name. And you can Google these, and that's how you know that you have an acceptable name. Okay, this is a quaternary, so 4,4-quaternary salt. And these get the IUM, inium. This would be inium iodide. Okay, so what is that? If you look at your heterocyclic compounds, you'll see that this structure here is piperidine. So piperidine. So this would be, you got 2 substituents here. Methyl, so it'd be N, N, dimethyl, piperidine, drop the E, and write IUM, iodide. Okay, this one here, this M plus O minus, it's actually a stable molecule, and it's called an amine oxide. And so that amine oxide would be, this could be called N-ethyl, see the ethyl group, N-ethyl, N-methyl, and that's benzene amine oxide. Okay, because that's an amine oxide. This compound here would be a tertiary amine. So you find the nitrogen, and an appropriate name would be make this a substituent and this a substituent. And what are you left with? What does that look like? That's aniline. So the name of that compound, come down here, would be N-ethyl, N-methyl, N-ethyl, N-methyl, aniline. This compound here would be also an ammonium salt. Well, IUM chloride. So that would be, that's pyridine, so pyridinium chloride. You've seen this in PCC, right? Pyridinium chlorochromate. This is the chromate. And this one here, you see the nitrogen. The nitrogen is bonded to 2 carbons. That makes it a secondary amine. You find your longest chain, including the nitrogen. So 1, 2, 3, 4, 5, 6. 6 is hexane, drop the E. 1, 2, 3, dash 3 amine. That tells you where the amine functional group is. And then what's your substituents? You have an ethyl here and an ethyl here. So this gets a number, 4 dash ethyl, and then dash N ethyl, hexane 3 amine. And it doesn't matter which one you add first. Okay, we're supposed to rank the amines in each set in order of increasing basicity. So first I would apply your rules and then check so you get familiar with using pKa values because they're available to you. You can use the pKa values. So the first one here, you have an aromatic amine. So I would say increasing basicity, so let's put increase, this be the most basic on this side, and this will go with least basic. So the most basic of these three in group A, you have a primary amine, and that's an aliphatic amine. Aliphatic amines are more basic than your aromatic amine. And you see this has 1 aromatic amine, and this one has 2. So the way I would rank this is I would put this aniline in the middle, and then the diphenylamine as my least basic. And if you check your pKa values, you'll find that aniline has a, or pKb, 9.40, and this pKb of a primary amine be 3.36. So what do we know? You decrease your pKb value, you increase your basicity. And I don't have a pKb value for this one, but it is the least basic. Okay, so let's go to B, set B. Once again, you see you have the aliphatic heterocycle. So I'd make that as my most basic. And here you have pyridine. I put pyridine next. And pyrrole would be my least basic. Pyrrole is actually acidic. So this is aromatic. You see how pyrrole has this lone pair here? So that's 6 pi electrons. That makes it aromatic. So what happens when you protonate pyrrole? Okay, so now pyrrole is protonated, and now it only has 4 pi electrons. This makes it so sad because that's anti-aromatic. Very destabilizing. In fact, if you look at the pKb here, the pKb for the protonated, or for pyrrole, is 15. pKb for pyridine, that's right, pyridine, is 8.75. And the pKb here, once again, secondary and tertiary primary amines are about the same. That's about 3. Okay, let's look at C. Once again, your aliphatic amine would probably be your most basic. You have pyrrole. Let's go with pyrrole being the least. So I'll put that over here again. And then that's pyrrole. And then you have an imidazole. Imidazole is something you see in biology a lot. So imidazole, and that has a pKb of about 7.05. Once again, your pyrrole has a pKb of 15, and then this has a pKb of 3. Let's look at D. We have aromatic amines all the way through, and so we have aniline, we have paramethoxy or paramethyl aniline, and then paranitro. So we've got to think about what electron withdrawing groups do and electron donating groups. So nitro, that's a positive nitrogen, and that would be electron withdrawing group. So this is deactivating, and you all learned that it's deactivating. This here is electron donating group because it's a methyl. So it's going to push electron density into the ring, making this nitrogen more negative. This one is it's pulling the rings into the lone pairs. So this is less negative nitrogen. And aniline is somewhere in between. So I guarantee you aniline will be the middle one here. So aniline is here. And then your electron donating should actually increase the negative charge on the nitrogen. Think about it. If it's more negative, it's going to go after the positive proton. That's what we're talking about here. How much affinity does these lone pair electrons have to take a proton? That's acid-base chemistry. And then, of course, your least would be the paranitroaniline. If we look up pKb values, we see that the nitro has a pKb of about 13. Aniline has a pKb of about 9.4. And then paramethyl has a pKb of 8.7. We have one more group. Yes, we have the E. So what do we have here? We have this, so let's classify this as aniline. This is benzyl amine. That benzyl group, that's a primary amine. Not only is it a primary amine, it's very activated because it's a benzyl primary amine. That is definitely going to be your most basic. Let's go ahead and put this here. This is a benzyl primary amine. And then this is an amide. And amide protons are not very basic because those electrons, if you look at the electrons that are on the amide proton, they're actually an sp2. So that's an sp2 nitrogen. If you draw the resonance structure here, you see that that nitrogen has a positive charge because those electrons can go into the oxygen. You also have the aromatic group. So that's going to be your least, and then that puts aniline in the middle. As you see from the previous problem, that the pKb for aniline is 9.4. Your primary amine will be about pKb of about 3. And then, well, it says benzylamine, it's actually 4.7. Okay, so 9.4. And then your amide, it will be your least basic. Okay, moving on to problem number 3. we need to be able to draw the acid-base chemistry here. So here we have pyridine, and it has those lone pairs, and it would deprotonate this acetic acid, and those protons would go there. So what would our product look like? You deprotonate the pyridine, that's nitrogen positive, and you deprotonate the acetic acid. Okay, so that is your reaction products. And then you have to look at this hydrogen here. So the pKa of acetic acid is about 4.9. It's just easier to do it in pKa's. And then the pKa of a protonated pyridinium ion would be about 5.21. So do you remember that the equilibrium lies towards your weaker base, weaker acid, which will have your higher pKa value. So your equilibrium is going to be towards the 5.21. So in this, products are favored. Okay, going to the next one. So the pyro lone pairs protonate the acetic acid, and then you get your pyrrolinium ion plus your acetic acid. All right, now you're talking about which proton, this or this proton. So the acetic acid proton, pKa of 4.9. Now the pKa of protonated pyrrole is -1. So when you're comparing -1 and 4.9, in this one, the reactants are favored. All right. The next one, you have pyridinium chloride and piperidine. So it's these lone pairs on the piperidine that are going to deprotonate that proton. So when you draw your product, you take the proton off of pyridine and you add it to piperidine. Piperidine is a strong base because it's an aliphatic. So the pKa of a protonated piperidine would be 11.2, and we're talking about this proton here. As one gets deprotonated, the pKa of that one is 5.21. So we compare what's larger, 5.21 or 11.2? Yes, so the weaker base would be products favored. Okay, the next one is aniline chloride. So the lone pairs on pyrrolidine will deprotonate the aniline proton, and you redraw aniline, just plain old aniline, plus your aliphatic pyrrolinium. Now it's pyrrolinium ion, and we are comparing the pKa values of this proton here, the one that got extracted. So the pKa there would be 4.6 if you look at protonated aniline compared to the pKa of protonated pyrrolidine. That's 11.27. So once again, the stronger base or the weaker acid is going to be your aliphatic amine. So in this case, products are favored. Okay, now we're into reactions. So make sure you understand acid-base chemistry of the amines, because amines are your organic bases. Okay, this is a direct alkylation reaction, and you all learned about this on Friday. So this is also an SN2 reaction. So your product will be phenyl CH2, 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 NH2, primary amine. Okay, the next one here is What's the name of this? Okay, 1-bromopentane. Let's draw 1, 2, 3, 4, 5. And there's our bromo. And we're reacting this with sodium azide. You also learned about this. This is SN2 reaction. So we should be able to draw the mechanism of an SN2 reaction. And that's going to be azide. You can just write N3. Make sure you have the right number of carbons. 1, 2, 3, 4, 5. And then lithium aluminum hydride. And then with a aqueous acid workup, we'll reduce an azide to a primary amine. That will always happen. So you can just go ahead and draw that 1, 2, 3, 4, 5, and then NH2. Okay. The next reaction we discussed in class on Wednesday. So this is exhaustive alkylation with excess CH3I. So we have a tertiary amine. So a tertiary amine will do an SN2 reaction. Its lone pairs, alkyl halide to get CH3 plus iodide. And then the second thing, we react it with silver oxide, Ag2O. And what that does is it basically exchanges the iodide for OH, and then when you add heat, you do a Hofmann elimination. And so you got to find your beta carbons. So if this is alpha, this is a beta carbon. Alpha, that's a beta. Alpha, that's a beta. Alpha, that's a beta. And only the beta hydrogens can be abstracted. So you can pretty much take any of those because your product has to be the least substituted. So that's a disubstituted. That would be a disubstituted. Any of those would be disubstituted. So that is your product. Okay, so let's go for this one up at the top here. We're taking, okay, we talked about this, but I told you really only worry about the arene. Remember the arene diazonium salt and how that's your intermediate. And you have aniline to then make 6 different products. Well, here you have a secondary amine, and you have NaNO2 nitrite and HCl. So what will happen is you're going to form see, did I do this reaction? Okay, I'm recording. Okay, so this one, we're not even going to worry about it. I told you you didn't need to know that one. Okay, so if you really want to know about it, we can talk about it offline here. Okay, so the next reaction is the nitrobenzene, zinc, and HCl. We've talked about that in previous chapters. That will reduce your nitro group to the amine. In this case, that's an aniline. Okay, the next reaction here, CH3NH2, that's methylamine, it's a primary amine, plus this acid chloride. Pyridine just keeps the reaction from building up HCl. So what happens is it takes the proton and binds up the chloride, so it keeps the reaction conditions being basic. You need the reactions to stay basic because this lone pair, the nitrogen, needs to be free. So when nitrogen attacks the carbonyl, those electrons go up, and you basically get NH2CH3, and then these electrons come down and the chlorine leaves after you get your tetrahedral intermediate, and that makes an amide. So that's N-methylamide is your product. And then the last one in this group is product from the above reaction. So now if you reduce it with lithium aluminum hydride and then do an aqueous acid workup, you can reduce an amide to a primary amine. So just make sure your carbons are the same number. So you got 1, 2, 1, 2. Well, in this case, it'll be a secondary amine. NHCH3. So in this case, you would reduce that to a secondary amine because the nitrogen is substituted in the amide. I don't know if you can see that very well here. When you count your carbons, 1, 2, 3. 1, 2, 3. Okay, looking at these here, we have an amine is your starting material, and lithium aluminum hydride. So this is just going to reduce that to NCH3. So that's a secondary amine. Okay, in this reaction here, the nitrile is going to get reduced to a primary amine. So nitriles also get reduced, so CH2NH2. Make sure you have the same number, 1, 2, 3, 4. 1, 2, 3, 4. So that's a secondary amine there. This reaction here, we haven't talked about it until Monday. We started reductive amination. You can go ahead and read ahead, but you should know 2-butanone diethylamine. So this is going to form an N-amine. We talked about that in last chapter, so you're going to minus water, the oxygen. Actually, it's going to form an N-amine. Well, your book actually forms an aminium salt. Okay, so we'll go with an aminium salt, and that's your intermediate. And then this is sodium triacetoxyborohydride, so it's mild. You also see sodium cyanoborohydride for this, but this is your secondary amine. So it reduces this amine, I-M-N-E, an amine to a tertiary amine. So the amine forms an amine, and it goes to an amine. Okay, so the next reaction is 3-nitroaniline. You need to know this one. So there's aniline, and 1, 2, 3. I think this is on your quiz. HCl and sodium nitrite forms the arene. Should be nitro there. With the amine, it forms a triple bond nitrogen. This is the arene, the aromatic ring, diazo, because 2 nitrogen, diazonium salt. And then the second reaction, copper bromide, will replace the N2, that's a great leaving group, nitrogen, with the bromide. We just redraw this nitro at the third position, and a bromide substitutes that nitrogen leaving group. That's the Sandmeyer reaction. Okay, the next one is 2-butanone you have potassium cyanide and HCN. These are not the most friendliest reagents to use, but that makes a hydrogen cyanohydrin. And then when you reduce it with lithium aluminum hydride, you're going to make a beta hydroxyamine. So this is the way you make beta hydroxyamines. So the OH stays the same, but now this nitrogen here, carbon, becomes CH2NH2. So there's your alpha. This is your beta, because the nitrogen, you count from the nitrogen, alpha, beta. That's your beta hydroxyamine. Okay, our next reaction is cyclopentanone. Here's cyclopentanone, and you react it with aniline. So what happens when you take an amine and a ketone? Okay, I'm going to draw it over here. We're going to make minus water. Okay, so we're going to connect the nitrogen with a double bond here. We lose water. This is an amine, okay? And then we're going to reduce it with LAH. So lithium aluminum hydride will then supply the hydride to make this NH secondary amine. Is your product. Okay, and the last one, draw that down here. We have 2-bromopentane. So that's 5. 1, 2, 3, 4, 5. Bromo, it's a 2. We're reacting this with trimethylamine. This is going to do an SN2 reaction. So that product is NCH3CH3. That makes a ammonium, it's an ammonium bromide salt. And then you're reacting it with silver and heat. And silver likes the halides, so that's going to precipitate out, and you're going to get the OH minus instead of the bromide, and then you look for your beta carbons because this is going to be a Hoffman elimination. Hoffman eliminations always make an alkene. So this is your alpha position, so here's beta, and here's beta. So you want to extract the hydrogen from the least substitute. This is going to give you the least substituted product. So which one will that be? So it will the OH will extract that proton, and this will leave. So you're going to lose your NCH3, and your product is going to be the least substituted 1, 2, 3, 4, 5 alkene, which is your Hoffman product. Okay, so these compounds are using the toluidine, and we're looking at the toluidine chemistry here. Let's just fill in our reagents. Okay, so the first one here, can't really see it, but you go from an amine to a nitrile. And so the way to do that is the sodium nitrite and HCl. And then you want to react that with copper cyanide. That's the Sandmeyer. Okay, this next reaction here, you are adding an extra carbon here. So the best way to do that is, once again, make a diazonium solid by sodium nitrite and HCl. And this time you're going to add CN just like you do there, and that's going to copper cyanide. But this time you're going to have to reduce it with the lithium aluminum hydride, an H3O+. And then that'll reduce a cyanide, a nitrile, to a primary amine. This reaction here, sodium nitrite and HCl once again, and then Ki. And that will substitute your the diazo salt for an iodide. Okay, let's come back over here. How do you make the phenol? Once again, you got to do sodium nitrite and HCl to make your diazonium salt. And then you're going to react this with reagents for this one, H3O plus, and you would just warm it, and that's going to make a phenol. This one here, you notice you have added a nitro group, and it's para to the amine. The amine has lone pairs, so that would be activating. The methyl group is activating, so it makes sense that you could get a para and ortho. So this is just sulfuric acid and nitric acid. And remember, that's the nitration reaction where you get your nitronium ion electrophile. This one here, we're going to react it with an SN2 reaction with this alkyl halide. Actually, that wouldn't be the best, okay, because you could get over-alkylation. Let's do a reductive amination. So if you remember reductive aminations, you have to have either a ketone or an aldehyde. So we're going to react this with a ketone. Let's draw that product with the aniline. You're going to lose water and make the imine, I-M-I-N-E, and then you do reduct. See, it's amination. You reduce it. So the next reagent you have to add is like sodium borohydride, or you can add lithium aluminum hydride and a little bit of acid to make that product. Okay, you have to add necessary reagents to show how you accomplish the following synthesis. Okay, the first one, just write down one up here. First you need to add nitrogen to the ring, so you know how to do this by sulfuric acid and nitric acid. That's the nitration. And then you're going to get a nitro group on the ring. So we'll just draw that there. So you get a nitro group, and then you need to reduce that. So the second thing you're going to do is add, how do you reduce it? Zinc and dilute HCl. And now you have an aniline. Now once you have an aniline, you can acylate that, A-C-Y-L-A-T-E. So this would be your acylating agent here, that portion. That's an acid chloride. And you add a little bit of pyridine to soak up your HCl. And that will give you your desired amide. Notice that that is an amide. Okay, the second reaction, we'll go across here. Pyridine, and you made a sulfonate. So basically, you just want to react this with sulfonyl chloride. This is also considered an acylation. And you always want to add a little bit of pyridine to soak up the HCl that's added. Okay, let's go to 3 over here. This is an elimination, and so let's go with a Hoffman elimination. So number 3, you need to add CH3 iodide, and then silver oxide, and then you want to warm that up. So let's just draw that reaction out. The first thing you're going to do is you're going to make this tertiary salt, or quaternary salt, which is going to make a good leaving group. And then the silver oxide is going to replace the iodide to make O-. And you got to look at your beta carbons. So That's alpha, this is beta, this is theta. So in this case, this OH has abstracted this hydrogen, and this is now a leaving group, and you have ring opening. 1, 2, 3, 4. 1, 2, 3, 4. And then it forms a double bond, and it's this reaction bond that actually breaks. That is your product. Okay, going to the next one, 4. You go from a ketone to an amine. The best way to do this would be just using ammonia, and or you could use hydroxylamine, NH2OH, and then you would reduce that with lithium aluminum hydride or sodium borohydride. I think your book uses lithium aluminum hydride and then does the acid workup. That's reductive amination whenever you go from a ketone to an amine. Okay, this problem here, you're going from a primary amine to an amine oxide. And if you remember the slide, we showed that would be an oxidation. So you need to add an oxidizing agent. Hydrogen peroxide would do that, and you would want to keep it cold. It's just H2O2. Okay, number 6 here. As you can see, this would be a cope elimination. And the reason why you know it's a cope elimination uses an oxidation. It does an oxidation before it does an elimination. And the oxime here shows you that you oxidize the amine. So how do you do that? You do that with hydrogen peroxide, and then you add heat. And what happened was, this is your beta carbon, and that OH then would do it's a 5 carbon or a 5 atom ring, and it would do the elimination there to break that bond. And that would be a cope elimination. Okay, the last one here in this set is how to make this mosquito repellent. And you have a carboxylic acid, and you want to go from the carboxylic acid to this amine. So basically you'd want to react this with thionyl chloride. That is going to make your acid chloride, and then you'll react it with 2 molecules. Well, actually, you might as well just go with the one in diethylamine, a little bit of pyridine, and that is an acylation reaction of an amine to give you your product. Okay, the next problem is that these drugs were made using these synthetic routes, and these synthetic routes to make these amines would be, so let's look at the first one, phenacetin, and you're supposed to do no more than 6 carbon atoms. Okay, so you see this first, this is an ether, right? That's an ether. So Williamson ether synthesis is how you can do that. And basically the best way to do that would be through a phenoxide. And then you would react that with CH3, CH2 bromide. So primary alkyl halide with sodium ethoxide or some kind of alkoxide. That is your Williamson ether synthesis. And then we have this portion of the molecule that would be electron donating group, which is activating, and it would activate the pair position. So at this point now we need to make a nitro group. So H2SO4 and HNO3, nitric acid, will nitrate that position. And then we would have to do reduction. So basically dilute HCl and zinc makes the amine, and then you do an acylation reaction where you react that with acetyl chloride for some pyridine. All right, the next one, methamphetamine. So retrosynthesis, when you're looking at this, you can have the benzene ring here, and we could do a Friedels-Crafts acylation, and then so let's look at that. So we go from we're going to go with benzene and our Friedels-Crafts acylation. Um, so you know when you do Friedels-Crafts, you need aluminum trichloride and an acid chloride. So 1, 2, 3, 1, 2, 3. But you're not going to have that ketone there, so you're going to have to do something like this with protecting groups. So you're going to have to do an acetal. So you actually use this molecule to do your Friedels-Crafts acylation, and then you would have something that looks like this, and then you could add H3O plus in water to hydrolyze that ketone, and then you would have to protect the other ketone, and it would react faster. So you'd have to then reprotect using this this ethylene glycol and an acid. And then at that point, you could do reductive amination because you have a ketone, and so this is your primary amine that you could react with this ketone, and then you reduce it with lithium aluminum hydride. And then after that, then you would want to work it up with acid and water, and that would give you your product. Oh, actually, you still have to, you would have this product, right? So you'd have your amine, but now you have to decarbonylate. So decarbonylation reaction, you learned 2 of those. You could do basically Wolff-Kishner with hydrazine, N2H4, KOH, and heat. Would probably be the best. Okay, the next one here is dopamine. So how would we do dopamine? The way I would do dopamine is I would start with my phenol, that's 6 carbons, and I would go ahead and do a Friedels-Crafts. So I would activate this with sodium hydroxide to make it faster, more donating, and then I would react it with a molecule such as this. It has 2 carbons and aluminum trichloride, and that is going to give you something that looks like this, and that gives you your 2 carbons that you need, and then you can reduce that down but actually before you reduce that down, you'd want to react it with the Wolff-Kishner reduction conditions because you need to decarbonylate. At this point, though, before you decarbonylate, you got to look at what. So that would be meta. I think you're okay. Okay, so go ahead and decarbonylate. Shouldn't be a problem. Okay, so Wolff-Kishner reduction, you've got this product now, and then you need to also add H2SO4 and HNO3 so you can make the nitro group, and that would be the OH is more activating than the methyl, so you can make that go ortho, and then you'd want to reduce that with zinc and dilute HCl. And once you do that, you have an amine, and then you can do the reaction with HCl and NaNO2, sodium nitrite, and then warm it with H3O+, and that will convert your amine into another OH, another phenol. And then at the very end, you can reduce this with lithium aluminum hydride and make the reduction of the nitro group to an amine. And that should give you your product. Look at the product structure. Yep, good. Okay, we got a couple more problems here. Number 8 is talking about reductive amination and how would you use reductive amination. So for A, draw out benzoic acid, and you want to make benzylamine. So let's draw out benzylamine. So how would you do that? Well, you're going to have to go to thionyl chloride, and that's going to make your acid chloride. And then you're going to need to react this with hydroxylamine. Actually, just react that with ammonia. And then you want to reduce lithium aluminum hydride. That's not actually going to work because you're going to reduce the OA benzyl group. Well, you could always also decarbonylate. That's kind of a tough one though, the benzoic acid. Let's do benzaldehyde. Benzaldehyde, this molecule here, you react it with ammonia, and you're going to make the amine. And then you can reduce it with lithium aluminum hydride to make the benzylamine. Okay, the next one is pyrrolidine. So that structure looks like this. This is pyrrolidine, and you're trying to make N-ethyl pyrrolidine. So that's what N-ethyl pyrrolidine looks like. So you need to react this with an aldehyde. 1, 2. Okay, and so that's going to make your amine. And then you can reduce it with lithium aluminum hydride, and that will make your product. Okay, D, cyclohexanone. So once again, you got a ketone, and you want to make N cyclohexyl pyrrolidine, which is a 5-membered ring. So the amine that you need to react that with is this right here, and you want to do lithium aluminum hydride and reduce that down. Okay, the last one here, we have actually the way I did this is I just basically took this 5 carbon, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, reacted with thionyl chloride, kind of what you do with acid chlorides, and then reacted with excess ammonia, and then lithium aluminum hydride and H3O+. Okay, so the next one, these do primary amines. Can't really see these here. Gabriel syntheses. And it's also talking about a nitrile, doing the Hoffman. So we're using these different syntheses to do the following reactions. So the first one is allyl bromide. So that's an allyl bromide. And we're trying to make an allylamine. So what you'll want to do, you'll want to do the Gabriel synthesis. This is a primary amine. So you can buy this thiamide salt. You can basically just buy the potassium thiamide. This is potassium thiamide, IMIDE, because this is an imide group, and nitrogen is in between 2 carbonyls. That's an imide. And this will do an SN2 reaction. And so now your allylic group is connected to this nitrogen. 1, 2, 3. I didn't draw that right. Count your carbons always. 1, 2, 3. Okay. Now you release it by reacting with hydrazine, NH2, N2H4, and some heat. And what that does then, the hydrazine replaces this group here. And then so now you have your NH2 allylic amine. Okay. Our next one is B. We are taking, really? Okay. We're taking this compound here, which is ethylbenzene, and we're trying to make this aniline, para-ethyl aniline. So the best way to do that, since that's activating, you can just react with sulfuric acid and HNO3. That's going to give you a nitro group there at the para position. And then you can react with zinc and dilute HCl, and that's going to reduce it to the amine. Okay, I have skipped C, so you can skip C. And let's go on to D. D, you want to do the Gabriel synthesis, so react this with your potassium diamide. And then the second thing you react it with is hydrazine into H4 and heat. And you will make your primary amine. Okay. The other way you could do it, you could react it with potassium cyanide. Actually, that's not true because then you'd have, but you could react it with sodium azide and lithium aluminum hydride. Potassium nitrile and then LAH will add an extra carbon. Okay, now we are on, is that all? D? Okay, so yeah, so one of them, let's see which one this one is. So this is 1, 2, 3, 4, 5, 6, 7. And if you want to do 4-phenyl 1-octamine, so what does that look like? 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4. So as you can see here, you've added one more. So this one you would definitely have to use potassium cyanide and lithium aluminum hydride. Okay, now for the last problem. Show how you would synthesize the following compounds starting with benzene, toluene, or alcohol. No more than 4 carbons. Assume that the pair is a major product. Okay, so the first one you're trying to make is pentamine. 1, 2, 3, 4, 5, and then your NH2. Okay, it's a primary amine. So you have a few primary amine syntheses. And so if you can do no more than 4 carbons, 1, 2, 3, 4, then you're going to start here. And you need to add 1 extra carbon and a nitrogen. The best way to do that is to make this an SN2 reaction. So you want to make this an alkyl halide. So the way to convert an OH to a bromine is PBr3. Remember that. It's a primary, so you don't want rearrangement. So now you got 1, 2, 3, 4, 1, 2, 3, 4 bromide. And now we can react this with potassium cyanide. And that's going to do an SN2 reaction. 1, 2, 3, 4, 5. And then you react it with lithium aluminum hydride. And you have your desired primary amine. Okay, the next problem is butamine. So let's go ahead and write 4 carbons. On the 1 you have NH2, and not really NH2 because you have an N-methyl. So go ahead and write the N-methyl, and that makes that a secondary amine. So to make secondary amines, I would think reductive amination. So you need to think reductive amination, and when you're thinking reductive amination, you need to think ketones and or aldehydes. So what we want to do here is 4 carbons, 1, 2, 3, 4. So, and we can start with an alcohol, that's right. We have to start with an alcohol. Okay, so starting with the same. In butanol, you can oxidize that, PCC. It's going to oxidize that to your aldehyde. And then 1, 2, 3, 4. Now you got to add in methyl. So react it with methylamine and then lithium aluminum hydride. Remember H3O plus, and that's going to make your desired product. You're going to make the amine, I-M-I-N-E, amine, and then you can reduce that down. Okay, and the next one, so draw your butylamine. It's on the 2, 1, 2, 3, 4. So there's the butyl with the nitrogen. You notice you got 2 substituents on the nitrogen. You got a propyl N-propyl, and you have an ethyl. So this is a tertiary amine. And you got to start with an alcohol. So let's start with this alcohol, the secondary alcohol. Let's oxidize it using PCC to the ketone. And now we can do reductive amination. And we can do reductive amination with we'll just go ahead and do it with this amine and lithium aluminum hydride. And that's going to give you your desired product. Okay, we have three more. We have benzyl and propylamine. So there's your benzyl group, and that should be a capital N. So there's your propyl. So the best way to do this would be we're allowed to use toluene. So we're going to take toluene, and we've got to make it an SN2 reaction. So this needs to be an alkyl bromide. So can you think of a reaction that can convert a benzyl group into a bromide? Yes, bromine and H-nu. So you can do free radical bromination of a benzyl group, and now you can react this with propylamine and then lithium aluminum hydride to give you your desired product through and since that's cheap, you could do that with excess. That should work. Okay. The next one is 3-propyl-aniline. Okay, so 3-propyl-aniline. So what does that look like? So let's draw aniline. 1, 2, 3. And there's your propyl. So you start with benzene, and you have to do a nitration. So sulfuric acid and HNO3. That's going to give you your nitro group. And that's going to be a meta director, right? And that's good because you need it at the 3. So the best thing to do then would be a Friedel's Craft, so aluminum trichloride and this propyl acyl compound. And then after you do that, that's going to give you your 3-nitro acyl compound. And then you're going to have to, at this point, you can do the Clemmensen reduction that you've learned. And that's mercury and zinc and dilute HCl. And those conditions would also reduce the nitro. So not only would your nitro get reduced to the amine, your carbonyl then would be deoxygenated to give you a methylene. All right, the next one is 4-isobutyl aniline, and this is going to be very similar. So let's look at what that looks like. There's your aniline, and this is your isobutyl. And you want to do the same thing. You want to you want to first make an amine. So you want to take your benzene group, and you need to react this with H2SO4 and nitric acid. That's going to do nitration, NO2. But then the next thing you want to do is go ahead and reduce that with zinc and dilute HCl. So that's going to go ahead and take it down to the amine because you need a para director. You need an activator. An amine would be a para director. So then you can react this to an Friedel-Crafts acylation, aluminum trichloride in your acyl group there. That's going to add now to your para position. And then you can do the Wolff-Kishner reduction. Y'all remember that? That's N2H4 hydrazine, KOH, and a high boiling solvent. The last one is an azo dye. So to do this azo dye, we're going to have to take benzene and you're going to have to react it in sulfuric acid and nitric acid to make the nitration, and then you're going to reduce that down to the mean using zinc and dilute HCl. And so then you're going to have your amine. But then the next thing you're going to do is you're going to react it with sodium nitrite and HCl, and then you can react this with a phenol. And so if you look, that's going to give you the diazo salt, which is a good electrophile, excellent living group. The phenol is activating group, para. So this will do, this is your electrophile, this is your nucleophile. So this will leave, and you get your product.